presentation with the help from the Funding Center of Aviation and Space Research and European Union. The topic of presentation is the temperature evolution as a factor parameter of this particular steel. Together with Matěj Mžourek and Papuga from Czech Technical University, we brought you this topic. So briefly, this is the outline of my presentation. I will say a little bit about the production of the specimen, then the measuring setup which we are using, the key factor in this presentation, the self-heating effect, and all the motivation behind it. So first of all, the motivation behind this is to speed up the creation of the SM curve using the temperature evolution instead of doing the SM curve as a standard, as it's done normally. So first of all, these are our specimen. It's probably not necessary to introduce these specimen. We have two hourglass specimen with different diameter in the active cross-section, and also two specimen which are rotated dot ones with different diameter in the active cross-section. The reason why we are using 4 different specimens is correlated with the critical volume of presentation that wasn't presented yesterday because of flight delay, but maybe in the paper you can read about it. But all the specimens are made from molybdenum steel. The roughness of the sample surface is achieved by turning followed by grinding. On the right downside you can see the specification from the tensile tests. This is our equipment. It looks obsolete, but it works perfectly. So this is a 100 kilonewton resonating pulsator, which works at the load control ratio of -1. In this case, tests are terminated by a frequency drop of 5 Hz, which is correlated with the drop of the specimen stiffness and crack initiation. Our main focus is on the fatigue testing in the regime between 5,000 cycles and 2 million cycles. On the downside, you can see the testing frequency, which are correlated to the sample stiffness. The temperature measuring is done by a thermal camera, as you can see on the right side. To make sure that we are measuring the temperature as correctly as possible, we are using high acidity coating, which is made in the Czech Republic at Labir and Western Bohemia. No product placement, but if necessary to say it. And here is the thermogram from the thermal measuring. Also, this needs to be pointed out that we are using we are measuring the loaded specimen, which is loaded by amplitude of load, and you can see the focus area in the middle. It varies with geometry of the sample, but there is also an unloaded specimen which can be used as a retraction of the deviation in the chamber where there is the testing is happening. So we are retracting the ambient temperature from the measuring by using the in vivo unloaded specimen. And the main motivation here is to use additional parameter for the fatigue experiments, which is called the self-heating effect. The self-heating effect occurs during the fatigue loading with the amplitude of load, and you can see that it develops in the 3 phases, as you can see here. The first phase can be characterized by initial incline, and the second phase can be characterized as a stabilized temperature. And also the third phase can be correlated with the crack initiation, and it leads to failure, as you can see here. But this is the ideal model, which wasn't really working in this case. In this case, as you can see on the right side, this is experimental data. This is only idealized model. That even for samples around high cycle fatigue, around 600,000 cycles, quite high amplitude, but over the fatigue limit, you can see that there is no stabilization during the whole lifespan of the specimen. So we were trying to mimic this evolution, which our main focus is on this intersection. So there is no reason to model this part more correctly, because we're trying to accelerate the test to make as much amplitude as possible, variable amplitude during the testing. Our motivation is to use estimate the fatigue limit. According to Risitano and Long, they were using a step test with a variable amplitude of load and trying to measure the stabilized temperature in such amplitude of load to correlate it with fatigue limit. They say that there should be a visible intersection of the stabilized temperature and with correlation to the amplitude of load, and there should be the transition between the fatigue limit area and over the fatigue limit area. But in this case, we are not able to use this method anyway because there is no stabilization, and also this method requires quite a differently behaving material. So we were trying to use the initial incline and the secondary incline from the whole test, as you can see here, from the whole lifespan. So these are the SMQ curves for our fatigue testing. So first of all, I would like to say that all the hourglass specimen, which are these odd numbers, these two lines, have a high performance in the regime of full cycle fatigue. But as you can see here, they come together, and the fatigue limit, which is established as a transition to the fatigue limit domain by cohort Baker progression, is quite similar all around the 500 megapascals. So these two parameters were input parameters for our analysis, and we tried to use a method to find the intersection more correctly, because this is mainly a graphical method which uses it's not really it depends on the person who's using this method, and it's not really robust to use for all the materials. So we were trying to use the finding the point where there is a radius of minimal, where there is maximal curvature or a minimal radius of curvature. By using this analytical expression, we approximated the evolution of the incline with exponential curve and find the roots of this find the maximal, or in this case minimal radius of curvature, and this brings us into the results that we got from this. On the right side, you can see the evolution of the initial incline for the dog bone specimen and for the hourglass specimen, and you can see that the active volume is leading to much higher increase in temperature. Also, it needs to be pointed out that here you can see the radius, here you can see the initial incline and the secondary incline for the fourth series, which is the dog bone specimen with the higher diameter in the active cross-section. As a result, we can see here that the fatigue limit from the Kohl-Becker progression was established at 480 megapascals, but the first or the only route that we got from the minimal curvature found the intersection of these two domains in the 565 megapascals area, which is an error of nearly 20%. But for the secondary incline, we can see that the radius of minimum curvature is found around 540 megapascals, which is quite high also And this method brings us an error between 10 to 30%, which is not really sufficient. The secondary method we were trying to use was a method by Fagione, which is based on the point that the area under the temperature evolution during the whole lifespan of the specimen under one single amplitude of flow could be taken as a material parameter. But in this case, we don't have the stabilization. So we are not able to say that the stabilization of temperature can be directly correlated to the amplitude of flow. You cannot do this prediction when you don't have the stabilized temperature. So only for this instance we're trying to evaluate this parameter to see if it's dependent on the amplitude of flow. And as you can see here, on the right side you can see that the limiting energy, which is the area under the temperature evolution, is highly dependent on the amplitude of load during the fatigue life testing. So I come to a conclusion that this material that we use is behaves quite unusual in this condition. This is mainly due to the fact that we are not able to change the frequency of loading. We are planning to do this test on hydraulic machine where we can adjust the frequency loading. Also, this method which we are using is unbiased to the person who's using it, but it brings up to the error between 10 to 30%. A better model for this method needs to be established, and also it needs to be said that probably the initial incline and the secondary incline are not the best parameters to observe in this situation. Also, it needs to be said, but it's fairly obvious that the Fagione limiting energy is not a constant number for this occasion. So, thank you, and these are my colleagues.
I didn't have to stand up. You were so much on time. Do we have questions from you? No questions. I should ask. So the previous talk was saying that we can actually detect damage using the change of resistivity, and now you're saying we can detect damage using thermal observation.
Thermal observation. This method was used on various materials in various places, and we were using this method to establish the fatigue limit for 3D printed aluminium with quite good successful results. But this particular material gives us a lot of problems, and that's probably why I was going to say something about it, because it's quite interesting that when something doesn't work, something will come up, some idea. So this is like the beginning of the.
So you're thinking about changing or developing something from the top of this line that I didn't know the name. Yeah, sorry.
Yes, because we use this method when there's the stabilized temperature. It's fairly easy, and it comes to quite good results because we're only observing the temperature on the sample surface. We're not applying any strain gauges or anything. And if this works sufficiently, it could approximate the SM curve quite well. I just don't know if I answered the question correctly.
No, it really wasn't the question. Yes, thank you very much.